Module 6, Lecture B, Text Models. By the end of this lecture, you will be able to use nn.Embedding to convert token indices into dense vector representations, build a simple sequence model, e.g. RNN or CNN, for text classification in PyTorch, and train and evaluate the text model on a labeled dataset, monitoring accuracy and loss. Working with embeddings, using embedding layers. Embedding layers in text models convert token indices into continuous vectors instead of leaving them as simple integer IDs. Starting from a vocabulary where each token has a unique index, the embedding layer works like a lookup table that maps each index to a dense vector of fixed size. You can think of this as a matrix where rows correspond to tokens and columns to features, and passing token indices through it retrieves their vectors. This transformation from discrete indices to continuous representations is essential for capturing subtle similarities and differences between tokens, and improves how the model processes them in later components, such as recurrent networks or attention mechanisms. Embedding layers start with random vectors that become meaningful during training. As the model learns from tasks such as sentiment analysis, gradients from the loss function adjust these vectors so that tokens appearing in similar contexts move closer together in the embedding space, while those in different contexts move farther apart. For example, in movie reviews, positive words like excellent and fantastic end up near each other, while a negative word like terrible is far away. This learned structure allows the model to capture useful semantic relationships for the task. Embedding layers reduce complex one-hot representations into compact, meaningful vectors, which makes models more efficient and expressive. This is especially important for very large vocabularies, such as those found in social media or legal text. By mapping each token to a smaller vector, models can process long sequences more easily and generalize across similar expressions. For instance, a system can learn that words like refund, reimbursement, and money back are related because their vectors are close to each other. In this way, embedding layers connect raw text to the continuous numerical forms that neural networks can understand. Python code using embedding layers. This script demonstrates a simple example of text embeddings. It uses TensorFlow to imitate how PyTorch handles embeddings. The main idea is to convert token indices into vector representations. These vectors can then be used as numerical inputs for further processing in machine learning models. A line that begins with an exclamation mark is a shell command used to install a specific TensorFlow version, in this case, version 2.20.0. It is not Python code, but a command that prepares the environment before the script runs. Specifying the exact version is important because different TensorFlow versions can have different features or behaviors. The script is designed to work with this particular version, so installing it helps ensure it runs correctly. We start by importing 3 key tools for our script. The operating system module lets us work with the system, such as managing files and environment settings. The random module provides functions for generating random numbers and performing random operations, which can help with tasks like setting seeds or creating random data. Finally, we import the numerical computing library NumPy, which we will use to handle arrays and carry out efficient mathematical operations throughout the program. We start by importing TensorFlow, a main library used for machine learning and deep learning. We also import the layers tools from Keras, which is built into TensorFlow, and provides high-level building blocks from neural networks. This setup lets us use different types of layers, including an embedding layer that turns token indices into dense vector representations. These imports form the basic foundation needed to build and train models in TensorFlow. We set a seed value, such as 42, to make all random operations reproducible. This means that every time we run the code, the random results will be the same. We apply this seed to Python's random number generator, to NumPy's random number generator, and to TensorFlow's random number generator. Using the same seed across these libraries ensures deterministic behavior in our experiments and makes results easier to verify and compare. This code prints the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility and understand why certain features or behaviors appear in your program. By displaying the version, you can quickly confirm that the intended TensorFlow release is installed and running in your environment. We create a small vocabulary as a dictionary that maps each word to a unique integer index so it can be processed by an embedding layer. This vocabulary includes a padding token, plus the words good, bad, and movie. The padding token is assigned index 0, and each of the other words gets its own distinct index. This mapping is essential for turning text into numerical form that machine learning models can use. This line displays the vocabulary mapping, which is a dictionary that links each word to a specific token index. This mapping is essential because it converts text into numerical form. Once in numerical form, the data can be passed into the embedding layer, which processes these token sequences for further use in the model. We begin by creating a small batch of token index sequences using a numerical array, where each row is a sequence of token indices. For example, one sequence might contain the indices 1, 3, and 0, and another might contain 2, 3, and 0, each referring to specific words in our vocabulary. These indices are stored as 32-bit integers, so they work smoothly with TensorFlow. This batch of integer sequences is then ready to be passed into an embedding layer, which will convert each index into its corresponding vector representation. In this step, we print the sequences of token indices that were prepared earlier to verify they are correctly formatted before sending them into the embedding layer. Viewing these sequences lets us confirm that the input data matches our expectations. This simple check is important for debugging and for understanding how data flows through the model. We start by finding the size of our vocabulary, which is simply the number of unique tokens in our dictionary and tells us how many distinct tokens the model can recognize. Then we choose an embedding dimension of 4, which is the length of the vector used to represent each token. This dimension controls how much information each token's vector can store, while balancing the richness of the representation with computational efficiency. Together, the vocabulary size and embedding dimension define the basic structure of our token representations. We use a Keras embedding layer in TensorFlow, which works like the embedding layer in PyTorch. It takes the vocabulary size, meaning the number of unique tokens, as the input dimension, and the embedding dimension as the output size, which sets how large each token's vector representation will be. The embeddings are initialized with values drawn from a uniform distribution. This layer converts token indices into dense vectors that can then be fed into the rest of the neural network for further processing. The model takes sequences of token indices and passes them through an embedding layer, which converts each index into a vector. This means that discrete numerical tokens are turned into dense, continuous representations. These vector representations are much easier for machine learning models to work with. This step is essential because it allows the model to learn relationships between words based on how they appear in context. This code converts the embeddings from a TensorFlow tensor into a NumPy array so they can be worked with more easily outside the TensorFlow environment. By doing this, you can take advantage of NumPy's tools for numerical operations and data analysis. In practice, this makes it simpler to inspect, manipulate, and process the embedding values. The code prints the shape of the embedding array, which tells you the dimensions of the embeddings produced after the sequences pass through the embedding layer. This shape shows how many tokens were processed and the size of each embedding vector. Checking it is a quick way to confirm that the embeddings have the expected size. This helps verify that the embedding layer is working correctly and producing vectors with the intended dimensionality for each token. We start by printing the embeddings for the first sequence, which means taking the first element of the embedded array. This element holds the vector representations for all tokens in that sequence. By examining these vectors, we can see the specific continuous values assigned to each token index. This helps us understand how the embedding layer has converted discrete token indices into points in a continuous vector space. This example shows that when the same token index appears in different sequences, it is always mapped to the same vector by the embedding layer. By comparing the vector for the word movie in two separate sequences, we see that its representation does not change. This consistent mapping is essential because it preserves the semantic meaning of each token across all sequences. In other words, the embedding layer ensures that the same word is always represented by the same vector. This script shows how to use TensorFlow to create text embeddings in a way similar to PyTorch. It first fixes random seeds so the results are reproducible, then defines a small vocabulary with a padding token, and prepares short sequences of token indices that represent simple sentences. An embedding layer is created with a vocabulary size matching the number of tokens, and an embedding dimension of 4, so each token index is mapped to a 4-dimensional vector. Passing the sequences through this layer produces a NumPy array of embeddings, and the script checks the shape of this output and prints the vectors for the first sequence. It also demonstrates that the same token index, such as the one for the word movie, always maps to the same vector across different sequences, showing the consistency of the embedding layer. Handling padding tokens. When working with text data and embeddings, it is important to handle padding tokens correctly so models remain reliable. Because neural networks train more easily when all sequences in a batch have the same length, shorter sequences are extended with a special padding token that has no real meaning. This allows efficient parallel processing, but it also introduces a risk. If the model starts treating these padding positions as meaningful, it can distort learning and harm performance on tasks like sentiment analysis or intent detection, where the true words and their positions matter. To prevent padding tokens from distorting a model's language understanding, we give them a special index and treat them differently in the embedding layer. This ensures that padding does not contribute to the model's learned representations, so only real words influence its understanding. For example, when shorter customer support messages are padded to match longer ones, the model will not mistakenly learn patterns from the padding. By fixing or ignoring the padding index, the model stays focused on the meaningful content, no matter how much padding is present. Handling padding tokens correctly is important for sequence models because these models combine information over time to make predictions. If the embeddings for padding tokens change during training, they add noise and disturb the model's internal state and pattern recognition. By treating padding as non-informative, the model can focus on meaningful content, such as emotionally important words or key terms. This leads to better generalization when working with inputs of different lengths and can significantly improve performance in real-world applications. Python code. Handling padding tokens. This material explains a script that highlights how padding token embeddings work. It uses TensorFlow to imitate the behavior of embeddings commonly seen in PyTorch. The main goal is to show what happens to the padding index inside an embedding layer and how it is treated differently from other tokens. By focusing on this behavior, the script helps clarify how padding is represented and handled in neural network models. The commented line is instructing you to install TensorFlow version 2.20.0. This ensures the code runs with that exact version, which may be required for compatibility. Using this specific version helps match the expected features and behavior of the library. It also helps prevent errors that could occur if a different, newer, or older version were used. We start by importing 3 key tools. The operating system module lets us work with the system, such as managing files. The random module gives us functions to generate random numbers, which is useful for tasks like sampling or shuffling data. Finally, we import NumPy, a numerical computing library that helps us handle arrays and perform mathematical operations efficiently. We start by importing TensorFlow, a library used to build and train machine learning models, and then bring in the Layers module from Keras, its high-level interface. This Layers module offers many ready-made neural network components that simplify constructing complex models. In this script, these imports are specifically needed to create and manage embedding layers for text data. A key focus is how these embedding layers handle padding tokens, so that the model processes meaningful text correctly. To make our results repeatable each time we run the program, we set a seed value of 42 for all the random number generators we use. We first apply this seed to Python's random module, so any random operations there are consistent. We then use the same seed for the NumPy random generator, so its random values are also reproducible. Finally, we set the seed for TensorFlow's random generator, which is especially important in machine learning because it controls how weights and other random processes are initialized. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because different versions may behave differently. This helps with ensuring compatibility and makes debugging easier. In this example, we define a small vocabulary that includes a special padding token, spoken as pad. We then build a dictionary that assigns each word in the vocabulary a unique integer index. The padding token is given index 0, and the words thanks and for are given indices 1 and 2. This mapping lets us convert words into numbers so that an embedding layer can process the text efficiently. We display the vocabulary mapping to show how each word is converted into an index, and we specifically point out which index is used for the padding token. This makes it clear which value represents padding in the data. Understanding this is important because the padding index is treated specially when working with sequences of different lengths in embedding layers. We create 2 short example sentences as sequences of word indices. The first sequence represents the words thanks and for, using a predefined mapping from words to numbers. The second sequence contains only the index for thanks. This gives us sentences of different lengths, which is typical in natural language processing. Using indices in this way lets us later convert the sequences into embeddings for further processing. To handle padding for a shorter sentence, we first fix the maximum sequence length to 2, so both sentences can be processed together. The first sentence already matches this length, so it stays the same. The second shorter sentence is extended by adding a padding token at the end. This padding token is represented by its index in the vocabulary, which makes both sentences the same length for batch processing. We combine 2 padded sequences into a single batch tensor by converting their index lists into a 2-dimensional NumPy array. This array uses 32-bit integers, so it will work smoothly with TensorFlow operations later. Creating this batch tensor lets us feed both sequences through the embedding layer at the same time, which makes computation more efficient and ensures the padding tokens are handled consistently. We first print the shape of the batch indices to verify their dimensions before performing the embedding lookup. This check confirms that the data is organized correctly and matches what the embedding layer expects. Ensuring the input shape is correct helps the embedding layer function properly and prevents shape-related errors during processing. We start by finding the size of our vocabulary, which is simply the number of entries in the dictionary that maps each word to an index, including the padding token. This tells us how many unique tokens our model can represent. We then choose an embedding dimension of 4, which is the length of the vector used to represent each word. This dimension controls how much information each word embedding can capture in the model's vector space. We define an embedding layer using TensorFlow's Keras tools to turn input word indices into dense vectors of a chosen size. The input dimension is set to the vocabulary size, so the layer expects indices from 0 up to 1 less than that size. The output dimension is the length of each embedding vector, which in this example is 4. We also enable masking so that index 0, usually used for padding, is ignored during training. Finally, we assign the layer a descriptive name, toy embedding, to make it easy to identify in the model. The code takes a batch of integer indices and passes them through an embedding layer, which looks up a learned vector for each index. This converts discrete token IDs into dense, continuous vectors. These vectors capture meaningful information about each token and form the representation the neural network will use. This embedding step is essential for preparing the input data for later layers in the model. We use a Boolean mask to mark which positions in the batch are padding rather than real data. This mask is produced by the embedding layer, which is set up to recognize the padding token. By distinguishing padding from actual data, later computations can safely ignore these padded positions. This is especially important when computing sequence-level statistics, so that padding does not distort the results. The code converts the embedded batch tensor and the mask tensor into NumPy arrays so they are easier to inspect in Python. Using NumPy arrays makes printing and examining their contents more straightforward. This conversion is mainly helpful for debugging and visualization purposes. The code first prints the batch indices, which are the numeric versions of the sentences, including padding tokens. So you can see how the input is structured before it goes into the embedding layer. It then prints a mask that marks which positions are real words and which are padding. This mask is a Boolean array that tells the model which tokens to pay attention to. It is essential because it lets the model handle padding differently from actual words during both training and inference. We are looking at the embeddings for the first sequence of tokens in a batch. The embedded data is stored as a numerical array, and by taking its first element, we isolate the embeddings for that first sequence. Each position in this sequence corresponds to one token, and its embedding shows how the model represents that token in a high-dimensional space. Examining these embeddings helps us understand how the model interprets and encodes the tokens in the sequence. We are looking at the embeddings for the second sequence in a batch, which includes a padding token. By selecting the second element from the embedded batch stored in a numerical array, we can see how each token in that sequence is represented in the embedding space. This includes both real tokens and the padding token. Examining these embeddings helps us understand how the model represents and handles padding within sequence embeddings. To make sure padding does not affect the mean of a sequence, we create masked embeddings. We first expand the mask so it matches the shape of the embeddings, then convert it to a float type so it can be multiplied with them. Multiplying the embeddings by this mask sets the padding positions to 0. As a result, only the meaningful parts of each sequence contribute to the calculated mean. To create a mean embedding for each sentence while ignoring padding, we first sum the embeddings across the sequence length so that only the content of each sentence is captured. We then count how many valid non-padding tokens each sentence has by summing the mask values after converting them to floating point numbers. Next, we divide the summed embeddings by this valid token count to get the average embedding for each sentence. A maximum operation is used on the count to prevent division by zero, ensuring a safe and stable masked mean representation that excludes padding tokens. Finally, the code prints the masked mean sentence embeddings, which are the average representations of each sentence after padding tokens have been removed. Converting these mean embeddings from a tensor to a NumPy array makes them easier to display and interpret. This output reveals how the model represents sentences while correctly ignoring padding, which is important for tasks such as sequence classification or translation. This script shows how TensorFlow embeddings handle padding tokens. It defines a small vocabulary with a padding token, creates two sentences, and pads the shorter one so both have the same length. These sentences are turned into index sequences and passed through an embedding layer that uses a mask to mark which positions are real tokens and which are padding. The script prints the indices, the mask, and the resulting embeddings, then uses the mask to compute mean sentence embeddings that ignore padded positions. This demonstrates how padding can be effectively excluded from embedding calculations. Initializing embeddings. When you set up an embedding layer, you choose both its size and how the vectors are initialized, which influences how well the model learns. The vectors usually start as small random values, so activations stay balanced, and each token in the vocabulary is assigned one of these random vectors with no initial semantic meaning. During training on tasks such as review classification, gradients from the loss function update these vectors. Over time, tokens that appear in similar contexts move closer together in the embedding space, turning the initial random table into a structured map of related words. Instead of starting with random word embeddings, you can often use pre-trained vectors learned from large text collections, such as news or social media. These embeddings already capture word similarities, so in tasks like sentiment classification, related words such as excellent and fantastic tend to appear close together. Using them usually speeds up training and improves performance, especially when you have limited data. To apply this, you match your model's vocabulary to the pre-trained one, copy over the available vectors, and initialize any missing words randomly so they can be learned during training. When choosing whether to keep embeddings fixed or update them during training, you need to balance stability and adaptability. Freezing pre-trained embeddings preserves their semantic structure and can reduce overfitting, which is especially useful with small or noisy datasets. In some cases, you might freeze most embeddings, but let a subset adapt to a specific domain. Fully fine-tuning the embedding matrix, on the other hand, helps the model learn task-specific nuances. A hybrid strategy, such as starting with frozen embeddings and later unfreezing them, shows that good initialization is important for guiding how the model learns. Python code, initializing embeddings. This script demonstrates how to initialize embeddings using TensorFlow. It focuses on creating simple embedding representations and examining their shapes and values. The goal is to understand how embeddings are set up, rather than to perform complex or intensive training. By running it, you can see how TensorFlow constructs and stores these embedding vectors. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is usually run in a Jupyter Notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available, so the script can run correctly. This helps maintain compatibility with the code that follows, which depends on TensorFlow to create and manage embeddings. We begin by importing a few standard Python libraries needed for the script. The operating system module is included for potential interaction with the system environment, even if it is not directly used later. The random module is brought in so we can generate random numbers and control them with a fixed seed when needed. Finally, we import NumPy, a numerical computing library that will handle arrays and perform mathematical operations throughout the script. We start by importing TensorFlow, a widely used library for machine learning and deep learning. After that, we print the TensorFlow version currently in use. Knowing the exact version helps check compatibility, debug issues, and reliably reproduce results. We set a fixed seed value, such as 42, to make random operations reproducible. First, we seed the standard random library so it always generates the same sequence of random numbers. Then we seed the random number generator in NumPy so its operations are also consistent. Using the same seed each time is important for debugging, verifying results, and comparing different runs of the code. We set the random seed for TensorFlow using a predefined value so that any random operations it performs give the same results every time the code runs. This makes the behavior of the model consistent across runs. Such reproducibility is important for running experiments reliably and for debugging issues effectively. We begin by defining a small vocabulary that includes a padding token, a few example words like two animals, a fruit, and a positive adjective. Each word in this vocabulary is mapped to an integer index. This mapping is important because it allows us to later create embeddings, which are numerical representations of these tokens. The specific words are not important. They simply demonstrate how different types of tokens can be represented as embeddings. We assign each word in the vocabulary a unique integer index by pairing every word with its position in the list. This creates a dictionary that maps words to numbers. With this mapping, we can convert text into numerical indices, which is required for embedding layers and other neural network components to process the data. The code prints a dictionary that maps each vocabulary word to a unique integer index. This dictionary was created earlier by pairing every word in the vocabulary with its own number. Viewing this mapping lets you confirm that each word is correctly linked to its intended index. This check is important because later steps, such as using embedding layers, rely on these indices being accurate. We start by finding the size of our vocabulary, which is simply the number of unique tokens in our list. This tells us how many different words the model needs to handle. We then choose an embedding dimension of 4, meaning each word will be represented as a 4-element vector. Together, the vocabulary size and embedding dimension define how we set up the embedding layer and how many features each word vector will contain. We define a new embedding layer using TensorFlow's Keras library to map integer token indices to dense vector representations. The input dimension is set to the vocabulary size, which controls how many distinct tokens the layer can handle. The output dimension is the embedding size, which determines the length of each vector. The embeddings are initialized with values drawn from a uniform distribution, and the layer is given the name random embedding, so it can be easily referenced later in the model code. To initialize the embedding layer, we start by creating a constant tensor containing the indices 1, 2, and 3, which act as example token inputs. We feed this tensor into the random embedding layer, which maps each index to its corresponding embedding vector. This process effectively builds the layer by defining how inputs are transformed into outputs. Once built, we can examine the shape and values of the resulting embeddings to understand how the layer is operating. The code prints the shape of the output produced by the random embedding layer to confirm that it is generating vectors with the correct size. By checking these dimensions, we can verify that the embedding layer is configured properly. This simple check helps ensure the layer is working as intended before using it in a larger model. We begin by accessing the random embedding matrix stored inside the random embedding layer, which holds the initial random weights for all embeddings. Next, we check the shape of this matrix to confirm its dimensions. These dimensions should match the vocabulary size by the embedding dimension. Verifying this shape ensures that the embedding layer is configured correctly and has the expected structure. We start by looking up the index of the word cat in the vocabulary mapping and use that index to retrieve its embedding vector from the embedding matrix. We do the same for the word dog. These indices act as pointers that let us pull out the exact vectors for each word. Once we have these vectors, we can analyze or compare the embeddings for these example tokens. We start by looking up the vector for the word cat in the embedding matrix using its index, which gives us its specific representation in the embedding space. We then do the same for the word dog, retrieving its corresponding vector from the same matrix. These two vectors provide numerical representations of the words cat and dog, which we can then analyze or compare within that shared embedding space. We create random vectors for the words cat and dog and round their values to 3 decimal places using a numerical rounding function. This rounding gives a clear, compact view of each vector's components. By printing and comparing these rounded vectors, we can see how the randomly initialized embeddings for cat and dog differ or resemble each other in the embedding space. We begin by creating a zero-filled matrix whose size is determined by the vocabulary size and the embedding dimension. Each row of this matrix represents a word in the vocabulary and serves as a placeholder in a simulated pre-trained embedding space. Initializing everything with zeros gives us a clean starting point, so we can later manually assign semantic patterns to specific words. This setup lets us fully control the initial state of the embeddings before loading or defining more meaningful values. We are manually defining simple semantic patterns in a pre-trained matrix by assigning specific vectors to words. For the word cat, we give it a vector where the first 2 dimensions have high values and the last 2 are 0, indicating that the first 2 dimensions are strongly linked to the concept of cat. We then do something similar for dog, giving it a vector with slightly different but still high values in the first 2 dimensions and zeros in the others. This setup makes cat and dog close to each other in this semantic space and highlights that the first 2 dimensions are important for both concepts. Here we assign a specific 4-dimensional vector to represent the word banana in a pre-trained embedding matrix. The vector has the values 0, 0, 1, and 0.8. This choice places banana in a particular region of the embedding space that is distinct from other types of words such as animals. It does this by giving more weight to the 3rd and 4th dimensions of the vector. We assign a vector to the word excellent in our pre-trained matrix so that it appears near animal-related words in the embedding space. This vector has the values 0.8, 0.7, 0.2, and 0.1. These numbers are chosen to encode a semantic relationship, placing excellent closer to words like cat and dog in this simplified example. Here, we set the embedding vector for the padding token to all zeros by assigning a 0 array at its position in the pre-trained embedding matrix. The length of this 0 vector matches the embedding dimension. Doing this makes sure the padding token carries no information in the embedding space and remains a neutral placeholder in the model's input. We define an embedding layer in TensorFlow Keras that uses pre-trained weights instead of random initialization. The input dimension matches the vocabulary size, meaning the number of unique words, and the output dimension is the embedding size, which is the length of each word vector. The embeddings are initialized with a constant initializer that loads the pre-trained matrix we created earlier. We set the layer to be not trainable, so these pre-trained embeddings stay fixed during training. Finally, we assign the layer the name pre-trained embedding, so it can be easily referenced later. To build the pre-trained embedding layer, we first call it with some dummy index values. This initializes the layer and generates the output vectors that correspond to those indices. Using these placeholder inputs lets us simulate real data, check that the layer works as expected, and examine the embeddings it produces. The code prints the shape of the output produced by the pre-trained embedding layer. By checking these dimensions, we confirm that the layer is generating vectors of the expected size. This verification shows that the embedding layer is correctly configured and aligned with the input setup. We start by looking up the vector for the word cat in the pre-trained embedding matrix using its index, which gives us its numerical representation based on learned semantic patterns. We do the same for the word dog, retrieving its corresponding vector. These word vectors capture how the model represents the meanings of cat and dog. Later, we can use these vectors to study how similar the words are and how they relate to each other in the embedding space. We now look at the pre-trained vector for the word cat, which shows the specific numerical values that represent cat in our predefined semantic space. Then, we examine the pre-trained vector for dog so we can compare its representation to that of cat. By viewing these two vectors side by side, we can see how the model positions cat and dog relative to each other in the embedding space, reflecting their semantic relationship. This function computes the cosine similarity between two arrays. It first converts both arrays to a consistent float format, then calculates their dot product to measure how similar their directions are. It also computes the magnitude of each array and multiplies these magnitudes to form the denominator. The cosine similarity is then given by the dot product divided by this denominator. If the denominator is 0, the function returns 0 to avoid a division by 0 error. We now compare how similar the word vectors for cat and dog are in a pre-trained embedding space using cosine similarity. This measure looks at the angle between the two vectors and returns a value between -1 and 1. A value of 1 means the vectors point in exactly the same direction. By feeding the cat and dog vectors into this cosine similarity function, we get a single number that represents how similar they are in that embedding space. The code prints a summary line showing the cosine similarity between the pre-trained word vectors for cat and dog. This similarity value indicates how close these two words are in the semantic space defined by the embeddings. A higher value means the words are more similar in meaning. The result is rounded to 3 decimal places to make it easier to read and interpret. This script shows how to create and compare word embeddings in TensorFlow. It defines a small vocabulary, maps each word to an index, and builds 2 embedding layers, one with random values and one with manually designed semantic patterns. The code checks the shape of the random embeddings and then examines the vectors for the words cat and dog from both the random and the predefined matrices. The predefined embeddings are set so that related words, like cat and dog, are placed close together in the vector space. Finally, it computes the cosine similarity between the pre-trained cat and dog vectors to highlight their semantic closeness, and reports the TensorFlow version, the vocabulary mapping, the embedding shapes, and the similarity value. Text sequence models. Recurrent layers overview. Recurrent layers in neural networks, such as RNNs, GRUs, and LSTMs, are built to handle sequences by processing one step at a time, while keeping a running memory of past inputs. At each new token, they update a hidden state that combines the new data with a summary of what came before. This makes them well-suited for language tasks because they can capture both local word relationships and the broader context. As a result, the final hidden state can serve as a compact representation of the entire sentence. In text classification, recurrent layers serve as sequence encoders that turn sentences of different lengths into fixed-size vectors for a classifier. In a sentiment analysis model, the text is tokenized, converted to embeddings, and passed through a recurrent layer that can emphasize important phrases and handle negations. The final hidden state, or a combination of states, is then fed into fully connected layers to predict categories such as positive or negative sentiment. Because their parameters are shared across time steps, recurrent layers naturally adapt to a wide range of sentence lengths and structures. When building text models in tools like PyTorch, choosing the right recurrent layer means balancing how much context the model can capture with memory use and computation time. Simple RNNs are easy to work with but often fail on long sequences, so they are less suitable for tasks like classifying long legal documents. LSTMs and GRUs use gating mechanisms to control what information is kept or forgotten, which helps them handle longer and more complex text, such as support tickets or spam messages. Overall, your choice of recurrent layer directly affects how well the model can process and summarize sequences under your training time and data constraints. Python code, recurrent layers overview. This material introduces a simple example of using recurrent neural network layers. It focuses on building a very small text classification model with a basic recurrent structure. The main goal is not high performance, but to help you understand how sequence processing works in practice. By following this example, you can see how recurrent layers handle input sequences step by step to produce a classification output. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0. It is typically run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available before running the rest of the script. This helps avoid problems, because different TensorFlow versions can change features or syntax and may not be compatible with the code that follows. We begin by importing a few standard Python libraries needed for the script. The operating system library is included for potential interaction with the system environment, even though it is not directly used in this short example. We then import the random library so we can generate random numbers and control reproducibility by setting seeds. Finally, we bring in the numerical computing library NumPy, which we will use to work efficiently with arrays and perform mathematical operations. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras, which gives us different types of neural network layers to build our models. Together, this setup lets us use TensorFlow's power while relying on Keras to streamline model development. We set a seed value of 42, so that any random operations in our code give the same results every time, which is important for reproducible machine learning experiments. We first set the seed for the standard random library, so its random numbers are consistent. Then we set the seed for the NumPy random number generator, affecting all NumPy-based randomness. Finally, we set the seed for TensorFlow's random number generator, ensuring that operations like neural network weight initialization behave the same across runs. This line checks and prints the version of TensorFlow currently in use. Knowing the exact version is important because different versions can change how the code behaves. It helps you confirm that your environment matches the requirements of your project. This makes it easier to ensure compatibility and to debug any issues that may arise. We begin with a small dataset of short text samples labeled by sentiment, where the first few sentences express positive feelings and the remaining ones express negative feelings. Examples of positive entries include statements like loving or enjoying a movie, while negative entries include statements about hating a movie or finding it terrible. This simple collection of positive and negative phrases will be used to train a basic text classifier. With it, we can explore how a recurrent neural network processes sequences of words to distinguish between positive and negative sentiment. We represent sentiment in our dataset using an array of integer labels, where each label matches a text sample. A value of 1 marks a positive sentiment, and a value of 0 marks a negative sentiment. This array is created with a numerical computing library and stored as 32-bit integers to keep processing efficient. We build a word-level vocabulary by starting with an empty dictionary and processing each text in our dataset. For every text, we split it into individual tokens and check each token against the existing vocabulary. If a token is not yet present, we assign it a new unique integer based on the current size of the vocabulary. By repeating this for all texts, we create a mapping from every distinct word to a specific integer, which allows us to convert text into numerical form for model training. The code prints the vocabulary mapping that was built from the text dataset, showing which integer index is assigned to each unique word. This output makes it clear how words are turned into numbers. Understanding this mapping is important because machine learning models work with numerical data rather than raw text. We begin by creating an empty list that will hold the tokenized versions of our texts. For each text, we split it into individual words and use a vocabulary dictionary to find the index for each word. These indices are collected into a list that represents the text as a sequence of numbers. We then add this sequence to our main list, so each original text is converted into a list of token indices based on the vocabulary mapping. To prepare sequences for a neural network, we first find the longest sequence so we know the maximum length needed. We then use Keras pre-processing tools to pad all shorter sequences up to this length, adding padding at the end. If any sequence is longer than this maximum, extra tokens are cut off. This process creates inputs that all have the same length, which is required for efficient batch processing in the model. Before building the model, the code checks and prints the shapes of the input data and the labels. The inputs are sequences of token indices, and the labels are the corresponding sentiment classes. Verifying that these shapes are compatible is essential because it confirms that each input sequence correctly matches a label. This simple check helps catch shape mismatches early and prevents errors during training and evaluation of the model. We begin by setting key hyperparameters for the model. The vocabulary size is defined as the number of entries in the vocabulary dictionary plus 1, to include a 0 index used for padding. The embedding dimension is set to 8, which is the size of the vector space representing each word. The recurrent layer then uses 16 units, which determines how much complexity and capacity the model has to learn patterns in sequences of data. We build a simple recurrent neural network for text classification in Keras using a sequential model which stacks layers in order. First, an embedding layer converts each word in the input sequence into a dense numerical vector using the vocabulary size, embedding dimension, and maximum sequence length. Next, a recurrent layer processes the sequence step by step, maintaining a hidden state that summarizes information from earlier words. Finally, a dense output layer with 1 unit and a sigmoid activation produces a probability that the input text belongs to the positive sentiment class, which is appropriate for binary classification. The model is now being compiled, which means it is being set up for training. It uses the Atom optimizer, a common and efficient choice for training large and complex neural networks. The loss function is binary cross-entropy, which is appropriate when the task is to distinguish between two classes. During training, the model will also track accuracy, so we can see how often it correctly predicts the class labels. The model is trained using a Keras fitting procedure that runs for 20 epochs, meaning it passes through the entire dataset 20 times. It uses a batch size of 4, so the model updates its weights after every 4 training samples. The training runs silently without printing progress. During this process, 1/4 of the data is set aside for validation, allowing the model to be checked on unseen data while it learns. The code checks how well the model performs on the training data by computing loss and accuracy using the model's evaluation function. This function takes the training inputs and their labels and returns performance metrics. The evaluation runs silently because the option to show progress is turned off. These results indicate how well the model has learned to make predictions from the training data. The code reports the model's final training performance by printing 2 key values. First, it converts the training loss to a float, rounds it to 4 decimal places, and displays it, showing how well the model minimized error during training. Then it does the same for the training accuracy, giving a rounded accuracy value that indicates how well the model predicted the training data. Together, these 2 numbers provide a clear summary of how effectively the model learned from the training set. We begin by defining a simple sample sentence that expresses a positive opinion about a movie. This sentence, which says that the speaker really enjoyed the movie, will be used to test the model's ability to predict sentiment. Because its structure is similar to the sentences used during training, it helps us evaluate how well the model can generalize to new but related inputs. We process the sample text by splitting it into individual words and looking each one up in a vocabulary dictionary. When a word is found, we replace it with its corresponding index from the dictionary. If a word is not found, we assign it the default index of 0. This converts the original text into a sequence of numerical indices that can be used as input to the model. We take the tokenized sample text and adjust it to match the input shape expected by the model. To do this, we pad the sequence to the maximum length used during training, adding zeros at the end when needed. Using Keras preprocessing for padding ensures that every input has consistent dimensions. This consistency is crucial, so the model can process the sample correctly and produce reliable results. The code uses the trained model to predict the sentiment of a prepared sample sequence. It calls the model's prediction function with this sequence as input, which returns the probability that the sample has positive sentiment. Because the result comes back as a nested array, the code takes the first element to obtain the actual probability value. This value is then converted to a standard floating point number, so it is easier to work with and interpret. We begin by displaying the sample text so we can clearly see the input being evaluated. Next, we show the model's predicted probability that this text has a positive sentiment, rounding the value to 4 decimal places for readability. This process provides a simple, clear summary of the model's prediction and makes it easy to quickly judge how the model performs on this specific example. This script builds a simple recurrent neural network in TensorFlow and Keras to classify movie reviews as positive or negative. It creates a small labeled dataset, converts words to integer indices using a vocabulary, and pads the resulting sequences to a uniform length. The model uses an embedding layer, a basic recurrent layer, and a final dense layer with a sigmoid activation to predict sentiment. It is trained with the atom optimizer and binary cross-entropy loss for multiple epochs, then evaluated to report loss and accuracy. Finally, the trained model is used to predict the probability at a new sample review is positive, illustrating the basics of sequence processing and sentiment analysis with a recurrent neural network. Convolutional text patterns. Convolutional text patterns focus on local language cues by looking at short windows of words rather than processing each word one by one. A convolutional layer uses learnable filters that scan over small word groups, similar to n-grams, and learn to detect patterns that are useful for predicting labels. For example, the model can learn that phrases like not good are linked to negative sentiment without being given explicit rules. By recognizing such key phrases wherever they appear in the text, convolutional models can efficiently support tasks like sentiment analysis and spam detection. Convolutional patterns in text are position invariant, meaning they can detect useful phrases no matter where they appear in a sequence. This is especially helpful in tasks like news classification or chatbot intent recognition, where important expressions may show up anywhere. The model reuses the same filters across the whole sequence, which makes it efficient in both computation and data usage. Over time, these filters specialize in recognizing particular word combinations, stylistic cues, and domain-specific jargon, leading to rich text representations that focus on meaningful patterns rather than memorizing exact sentences. Convolutional text patterns act like feature detectors that scan documents for short segments of text that support specific labels. In tasks like phishing detection, product categorization, or social media moderation, these detectors respond to key phrases or subtle word combinations that signal things like fraud, product type, or harassment. By using multiple layers and different filter sizes, convolutional models can capture both precise phrases and their surrounding context. This makes them especially effective for text classification problems where the most important information is concentrated in short pieces of the text. Python code. Convolutional text patterns. This script demonstrates how convolutional patterns can be applied to text. It builds a very small convolutional neural network that performs text classification. The main idea is to use filters that act like local n-gram detectors, capturing short sequences of words. The focus is on showing how these local filters help the model recognize useful patterns in text for classification tasks. The line with the exclamation mark is a shell command that installs TensorFlow version 2.20.0. It forces the environment to use this exact version of the library. Doing so helps ensure the code behaves as expected and prevents compatibility problems that could occur with different TensorFlow versions. We begin by importing a few standard Python libraries that we will rely on throughout the script. The operating system library is included for potential interaction with the system environment, even though it is not directly used in the visible code. We also import the random library so we can generate random numbers and control their behavior with a fixed seed. Finally, we bring in NumPy, a numerical computing library that helps us work efficiently with arrays and also manage random number generation. Together, these imports provide the basic tools needed for data manipulation and reproducible results. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras, a high-level interface that makes creating neural networks easier. We also import the layers tools from Keras, which provide components like dense and convolutional layers. Together, these imports give us the essential tools needed to construct and train our convolutional neural network model. We set a seed value, such as 42, to make random operations repeatable each time the code runs. First, we set the seed for Python's built-in random number generator, then for NumPy's random number generator, and finally for TensorFlow's random number generator. Doing this ensures that all random numbers, including the initialization of weights and other random steps in TensorFlow, are consistent across runs. This reproducibility is especially important in machine learning experiments, so results can be reliably compared and verified. This line of code displays the version of TensorFlow currently in use. It provides a quick check that the intended version of the library is installed and active. Confirming the version helps ensure that the code will run correctly and remain compatible with the rest of the project. We begin by creating a small text dataset made up of short sentences, where each sentence is a simple statement or opinion. This dataset will be used to train a text classification model. The sentences include both positive sentiments, such as strong expressions of liking a product, and negative sentiments, such as clear dissatisfaction. By including this mix of positive and negative examples, we help the model learn to recognize and distinguish different types of sentiment in text. We create a list of sentiment labels that matches each text entry in our dataset. Each label is either 1 for positive sentiment or 0 for negative sentiment. This list serves as the target variable for our text classification model. By training on these labels, the model learns how different text inputs are associated with positive or negative outcomes. We begin by creating a tokenizer using Keras preprocessing tools that can handle up to 50 unique words. This tokenizer converts raw text into numerical form so it can be processed by machine learning models. By limiting the vocabulary size, we focus on the most frequent words in the data. This helps control computational cost and can make the model more efficient and easier to train. The tokenizer is trained on the small text dataset by scanning the text and building a vocabulary of unique words. Each word is then assigned an integer index, usually based on how often it appears. These indices allow the text to be converted into sequences of numbers. This numerical form is essential for feeding the text data into a neural network model. The code turns each text in the list into a sequence of integers using a tokenizer that was previously fitted on the training texts. Each word is replaced by its corresponding index in the tokenizer's vocabulary. This step converts the original language into numerical form, which is necessary because the neural network can only process numbers, not raw text. In short, tokenization prepares the text data so it can be used as input to the model. We set a fixed maximum sequence length of 8 tokens, so that every piece of text we process is either padded or cut off to exactly that length. This creates sequences that are all the same size. Having a uniform length is important because the neural network expects inputs with consistent dimensions. Without this step, the model would not be able to handle variable length sequences efficiently. We use sequence padding so that all input sequences have the same length before they are passed to the neural network. This is done with a Keras preprocessing method that pads the sequences up to a specified maximum length, which is 8 in this example. The padding is added to the end of each sequence, so shorter sequences are extended until they match the chosen length. Making all sequences uniform in this way is necessary for the model to process them correctly. The code converts the list of sentiment labels into a NumPy array so they can be processed efficiently in numerical computations and used with common machine learning libraries such as TensorFlow. Using a NumPy array matches the input format these tools expect. The labels are also set to 32-bit integers to meet the model's requirements for binary classification. The code prints the shapes of the input data and labels to confirm that they are correctly formatted before training the model. By checking these shapes, you can verify that the features and labels line up properly. This step helps ensure that the model receives compatible inputs and can learn from the data as intended. We set the vocabulary size for text processing by taking the smaller of 50 and the number of unique words found by the tokenizer, then adding 1. This means the vocabulary is capped at 50 words, unless there are fewer unique words, in which case we use that smaller number. The extra 1 accounts for a special token that the tokenizer may need. This approach keeps the vocabulary limited while still covering all identified words and required special tokens. We build a simple convolutional neural network for text classification by first using an embedding layer that turns each word into an 8-dimensional vector based on the vocabulary size and sequence length of our data. Then, we apply a 1-dimensional convolutional layer with a few filters and a kernel size of 3 to detect local text patterns, using a ReLU activation to add nonlinearity. A global max pooling layer follows, which keeps the strongest response from each filter across the whole sequence, summarizing the most important features. Finally, a dense layer with a single neuron and a sigmoid activation outputs a probability that the input text belongs to the positive class, making the model suitable for binary classification. The model is designed with a clearly defined input tensor, so its architecture has a specific input shape based on the maximum sequence length. By setting the batch size to be flexible and the sequence length to this fixed maximum, the model knows exactly what size of input to expect. This preparation allows it to handle data of that fixed sequence length during both training and inference. As a result, the model can correctly process the input text and carry out the intended text classification tasks. We begin by running the model once on the first example from our input data so it has a clearly defined input tensor. This initial call is important because it sets up the model's internal structures and tells it what shape and type of data it will handle during training and inference. By passing in a small slice of the input, we simulate a forward pass, which builds the computational graph the model will use for later computations. When we compile the model, we prepare it for training by choosing how it will learn and how we will measure its performance. We use the atom optimizer because it is efficient and adapts well during training. The loss function is binary cross-entropy, which is appropriate for binary classification because it measures how different the predicted labels are from the true labels. We also track accuracy as a metric to see how often the model's predictions are correct while it trains. The model is trained using a fit function that takes the input data and their labels and runs for 20 epochs, meaning it passes through the entire dataset 20 times. It uses a batch size of 2, so the model updates its weights after every 2 samples. The verbose setting is turned off, so no training progress is printed. During training, 30% of the data is held out as validation data to monitor the model's performance. The code checks how well the model performs on the training data by using the model's evaluation function with the inputs and their labels. This function runs silently, without showing progress messages. It returns 2 main results: the loss, which measures how much error the model makes, and the accuracy, which shows how often it predicts the correct labels. These 2 values are then stored for later use. This code reports the model's final training performance by printing the loss and accuracy. It converts each value to a float, rounds it to 4 decimal places, and then displays it. Presenting these 2 metrics in a clean, readable form gives a quick summary of how well the model trained. We will use the example sentence, "I am not happy with this," to see how a convolutional layer processes text. By focusing on this specific input, we can examine the resulting convolutional feature map. This helps us understand how the model interprets the sentence and transforms it as it moves through the layers. In other words, This example serves as a concrete way to study what the convolutional layer is learning from the text. We begin by using a tokenizer to turn the example text into a sequence of integers, where each word is replaced by its index in the learned vocabulary. Then we adjust this sequence to a fixed maximum length by adding zeros at the end if it is too short. This padding step ensures that all input sequences have the same length, which the model requires to process the data consistently. To examine the outputs of a convolutional layer, we first locate that specific layer in the model, such as the second layer. We then build a new Keras model that keeps the same inputs as the original, but uses the convolutional layer's outputs. This setup lets us view the intermediate feature maps created by the convolution operation. By inspecting these feature maps, we gain insight into how the model processes and transforms the input data at that stage. We use the convolutional model to generate a feature map for the example input by passing the padded text sequence through its convolutional layer. During this process, we call the model's prediction function on the example input and turn off extra output so the prediction runs quietly. The result is a feature map that captures the activations produced by the convolutional layer for that specific input sequence. We print the shape of the convolution feature map to see the dimensions of the output produced by the convolutional layer for a given input sequence. This shape shows how many features are generated and how they are arranged. Understanding it is important for checking that the convolutional layer is set up correctly and that it produces the expected output size for each input. We examine the activation values from the first filter of the convolutional layer by printing its feature map. To make the values easier to interpret, we round them to 3 decimal places. We access the feature map for a single input example and focus on the channel that corresponds to the first filter. This lets us see how that specific filter responds to the input text through its activation pattern. The code uses the trained model to estimate how likely a given piece of text is positive. It sends the padded version of the example text to the model's prediction function, which returns a single probability value. This value represents the model's confidence that the text expresses positive sentiment. The code then converts this result to a standard number and prints it, rounded to 4 decimal places, to clearly show the predicted probability. This script builds a simple convolutional neural network in TensorFlow and Keras to classify short text reviews as positive or negative. It prepares a small labeled dataset, tokenizes the text, and converts it into padded sequences so all inputs have the same length. The model uses an embedding layer, a one-dimensional convolutional layer, global max pooling, and a final dense layer with a sigmoid activation for binary sentiment prediction, and is trained with the atom optimizer and binary cross-entropy loss. After training, it reports the loss and accuracy, examines the convolutional layer's feature map for a sample review, and then outputs the predicted probability that this sample expresses positive sentiment. Temporal pooling basics. Temporal pooling is a method for turning a sequence of token representations of varying length into a single fixed-size vector that a classifier can use. After recurrent or convolutional layers produce hidden states or feature maps over time, temporal pooling aggregates these into one consistent representation. This process summarizes information across all time steps or token positions into a single snapshot. For tasks like movie review classification, it condenses all patterns and cues from the entire review into one vector that reflects the overall sentiment, regardless of how short or long the review is. Temporal pooling summarizes information across time steps in a sequence. In average pooling, the model takes the mean of the hidden states over all positions, treating each time step equally to capture overall context. In max pooling, it selects the largest value for each feature, emphasizing the strongest activations. This is especially useful in convolutional models to detect key patterns, such as a single positive phrase in a review. Both methods help the model focus on important signals, even if they occur only once in the sequence. Advanced temporal pooling methods refine basic approaches so models better handle real-world language tasks. For example, combining max and average pooling can capture both strong local signals and the overall feature distribution. In recurrent models, using only the final hidden state may work for short texts, but pooling across all time steps is usually better for longer documents. This choice is especially important in applications like legal document classification or toxic comment detection, where the model must compress long sequences into meaningful representations. Python code temporal pooling basics. This script introduces the basics of temporal pooling using small sequences and simple tensors in PyTorch. It focuses on how to apply average temporal pooling to summarize information over time by taking the mean, and max temporal pooling to capture the most prominent values across a sequence. The goal is to clearly demonstrate these two core temporal pooling operations in a straightforward, minimal setting. We begin by importing the PyTorch library, which we use to work with tensors throughout the script. Tensors are multi-dimensional arrays that serve as the main data structure for our computations. PyTorch provides efficient tools to create, manipulate, and operate on these tensors. This tensor support is essential for performing the temporal pooling operations that the code demonstrates. We begin by setting a deterministic seed using the manual seed function in PyTorch so that any random operations in the script always produce the same results. This is important for reproducibility, especially in machine learning experiments that rely on randomness. By fixing the seed, we ensure that the same random tensors are generated each time, which makes debugging easier and helps us verify and compare results consistently. We create a small batch of sequences using PyTorch tensors, where each sequence is a list of token indices, and each index corresponds to a specific token. These sequences are stored in a two-dimensional tensor, with each row representing one sequence. A 0 is placed at the end of each sequence to serve as a padding token, which will later help us manage sequences of different lengths. This structure lets us process multiple sequences in parallel, making batch processing more efficient for machine learning tasks. The code prints the batch of token index sequences so you can inspect the raw data before any transformations or embeddings are applied. This step lets you confirm that the sequences are correctly structured and contain the expected values. By checking this early, you can catch formatting or data issues and better understand how information flows through the script. We create a small embedding layer to turn token indices into vector representations. The embedding dimension is 4, so each token becomes a vector of 4 numbers, and the vocabulary size is 10, meaning we have 10 distinct tokens. Using the embedding feature in PyTorch, each token index is mapped to its corresponding vector. This converts discrete tokens into continuous vectors, which is a key step for many text-based machine learning models. The embedding layer converts each token in a sequence from its index form into a dense vector of a chosen size. This means we move from simple discrete numbers to continuous numerical representations. These embedded vectors capture richer information about the tokens. This transformation is essential for later steps, such as pooling, because it provides a more informative and usable representation of the input data. We print the shape of the embedded tensor to verify that it matches what we expect. This shape is organized as batch size by time steps by embedding dimension. Confirming this structure is a quick way to check that the embedding process worked correctly. Once the shape is correct, we can confidently use the tensor for later operations. To handle padding in sequences, we first choose a padding token, which in this case is 0. We then build a mask by checking which positions in the sequence are not equal to this padding value, giving us a Boolean mask that marks the real, non-padding elements. Next, we add an extra dimension to this mask so that its shape matches the embedded tensor. This prepares the mask for later element-wise operations that will ignore the padding positions. We check that the mask has the correct shape to match the embedded tensor, with the same number of dimensions and an extra dimension of size 1 at the end. This ensures the mask can be broadcast properly over the embedded tensor. By confirming this compatibility, we can safely apply the mask without errors. This step helps preserve the integrity of the data structure for later operations that depend on the mask. We apply a mask to the embedded tensor to set the embeddings of padding tokens to 0. By multiplying the embeddings with this mask, we keep only the representations of real tokens and remove the influence of padding. This ensures that padding tokens do not contribute to later pooling operations. As a result, the pooled representation more accurately reflects the actual input sequence. To find the true length of each sequence without counting padding, we add up the mask values along the time dimension, since the mask marks all non-padding tokens. This sum gives the number of real tokens in each sequence. We then apply a clamp operation to force the minimum length to be 1, which avoids division by 0 later. This step is essential for safely and accurately computing averages during the pooling process. We apply average pooling over the time dimension of the embedded sequences to get a fixed size representation for each one. First, we sum the embedded token vectors along the time axis, while ignoring padding positions using a mask. Then we divide these sums by the previously computed sequence lengths. The result is an average embedding vector for each sequence that summarizes the contributions of all its valid tokens. To safely perform max pooling over the time dimension, we first make a copy of the masked embedded tensor. Cloning it ensures that any changes made during max pooling do not alter the original masked embeddings. This separate copy is then used to handle padding tokens correctly, so they do not interfere with the max pooling results. In this way, we protect the original data while still preparing it for effective pooling over time. Here, we prepare the tensor for max pooling by handling the padding tokens. We take the masked embedded tensor and replace positions that are all zeros with a very large negative value. This prevents those padded positions from being selected as maximum values during max pooling. As a result, the pooling operation effectively ignores padding and focuses only on the meaningful data. We now compute a max pooled representation across the time dimension by taking the maximum value of each feature over all time steps in the sequence. In practice, this means applying a max operation along the time axis of the tensor. The result is one maximum value per feature, which captures the strongest signal that appeared anywhere in the sequence. We ignore the positions of these maxima and keep only their values. This produces a fixed size summary that preserves the most prominent features from each sequence. We print the average pooled vectors to see how the average pooling operation has summarized each sequence. By averaging over the time dimension, this method compresses the sequence into a fixed size vector. The resulting vector represents the mean feature values across the entire sequence. Examining these vectors helps us interpret what information the pooling step has captured. The code outputs max pooled vectors which capture the strongest features from each sequence. Max pooling works by taking the highest value over time for each feature, so it keeps only the most prominent signals. This converts variable length sequences into fixed size representations, while emphasizing their most important elements. The final print statement summarizes the idea of temporal pooling, which is used to turn sequences of varying length into fixed-size summaries. This is important because many machine learning models require inputs that all have the same size. By applying temporal pooling, we capture the essential features of each sequence in a consistent format, no matter how long the original sequence was. This prepares the data for further processing or analysis by these models. This script demonstrates temporal pooling in PyTorch by turning variable-length token sequences into fixed-size vectors. It first embeds a small batch of token index sequences, then applies a mask so that padding tokens are ignored. Using this mask, average pooling computes the mean of only the meaningful embeddings, while max pooling highlights the strongest features by treating padding as very negative values. The resulting average and max pooled vectors show how temporal pooling summarizes information across time, either by capturing the overall average or the most significant features in each sequence. Training text models. Cross-entropy loss for labels. In training a text classification model, cross-entropy loss measures how wrong the model's predictions are so it can adjust its parameters. This loss function is well suited for multi-class tasks, such as predicting sentiment or topic. The model assigns a confidence score to each class, and cross-entropy compares these scores to the true label. The loss becomes small when the model gives high probability to the correct class, which smoothly guides learning and helps align predictions with the actual labels. Cross-entropy loss measures how wrong and overconfident a model's predictions are. If the model is very sure about an incorrect label, the loss is high. But if it is uncertain and spreads its guesses, the penalty is smaller. This pushes the model to be both accurate and appropriately confident in its predictions. As it trains on more data, it adjusts its outputs to reduce the average loss and increase the probability of making correct predictions. In text models that use cross-entropy loss, each training example produces a single loss value based on how the predicted class probabilities compare to the true label. These individual losses are averaged over a batch of examples, and this average guides the optimizer when updating the model's weights. By repeatedly minimizing this average loss, the model learns to assign higher probabilities to the correct labels. As a result, it becomes better at handling varied and noisy text data, such as different emotional labels in social media posts. Python code, cross-entropy loss for labels. This material introduces a simple example that uses cross-entropy loss in a tiny text classification task. The goal is to show how labels are handled and how the loss behaves in this setting. Rather than focusing on model complexity, it highlights the basic mechanics of applying cross-entropy loss to a small classifier. By examining this minimal setup, you can better understand how the loss function responds to different label predictions. In some setups, you may need to install TensorFlow before running your code. A comment in the script can remind you how to do this by showing a pip command for installing a specific TensorFlow version. This comment is not meant to be executed as code, but simply to guide you in preparing the environment correctly. We start by importing the operating system module to work with files and environment settings. Then we import the random module, which lets us generate random numbers for tasks like shuffling data or setting random seeds. Finally, we bring in the numerical computing library NumPy, which is essential for efficient array handling and mathematical operations in Python. Together, these imports prepare our program for file interaction, randomness, and fast numerical calculations. We start by importing TensorFlow, a powerful library for machine learning, and Keras, its high-level interface for building and training neural networks. We also bring in the layers tools from Keras, which provide the main building blocks for creating network architectures. With this setup, we can use TensorFlow's capabilities while relying on Keras to make model design and training simpler and more streamlined. We set a seed value, such as 42, so that all random operations in our code give the same results every time we run it. This means we initialize the random number generator in the standard random library, in NumPy, and in TensorFlow with the same seed. Doing this makes random numbers, random arrays, and things like initial neural network weights reproducible across runs. As a result, our experiments become easier to debug, compare, and verify because the behavior is consistent each time. This line displays the version of TensorFlow that is currently in use. It provides a quick check that the library is installed correctly. It also confirms that the script is running with the intended TensorFlow version. This helps avoid confusion when different versions may be present on the system. We begin with a small dataset made of short sentences, each expressing a sentiment about a movie or story. The first 3 sentences are positive, and the last 3 are negative. We use this simple collection to train a basic text classification model. This setup lets us study how cross-entropy loss behaves when the model is trained with different sentiment labels. We assign each sentence in our text dataset an integer label that represents its sentiment. A label of 1 indicates positive sentiment, and a label of 0 indicates negative sentiment. Using these labeled examples, we can train a model to recognize patterns in the text and automatically classify new sentences as positive or negative in terms of sentiment. We build a word index by starting with an empty dictionary that will store each unique word and its numeric code. For every sentence in our text data, we split it into words and check each word against the dictionary. If a word has not been seen before, we add it and assign it a new integer based on how many words are already stored. This creates a consistent mapping from words to integers, which allows us to convert text into numerical form for use in machine learning models. We begin by creating an empty list that will hold the numerical form of each sentence. For every sentence in our text data, we split it into words, and for each word, find its unique integer index from a vocabulary dictionary. We then collect these indices into a list, turning the sentence into a sequence of numbers. Each of these numerical sequences is added to our main list, giving us a complete numerical representation of all the sentences in the dataset. To prepare sequences for batch processing, we first find the longest sequence in the dataset and use its length as the maximum. This tells us how much padding each shorter sequence needs. We then apply a Keras preprocessing tool to pad all sequences up to this maximum length. Padding is added at the end so that every sequence has the same size, which is important for efficient model training. We convert the list of labels into a NumPy array of integers so it can be used efficiently by machine learning models which expect data in array form. By setting the data type to 32-bit integers, we store the labels in a format that is standard for categorical data. This format is widely supported in TensorFlow and other machine learning frameworks, helping ensure compatibility and efficient computation. Before building the model, the code prints the shapes of the input data and labels to confirm they are correctly formatted. This check verifies that the data dimensions match what the model expects. It also ensures that input sequences and their corresponding labels are properly aligned. Doing this helps catch formatting issues early and prevents errors during model training. We first set the vocabulary size by taking the number of unique words in our dictionary and adding 1 extra index to handle padding. Then we choose an embedding dimension of 8, which is the length of the vector used to represent each word in the embedding space. This embedding size is a tunable hyperparameter and can be increased or decreased depending on how complex the task is and how large the dataset is. To build a simple text classification model, we first create an input layer in Keras that accepts sequences of token indices with a fixed maximum length. We then add an embedding layer that converts each token index into a dense vector with a chosen size. The embedding layer uses the vocabulary size to know how many different words it can represent, and the embedding dimension to set the length of each word vector. This structure lets the model learn useful numerical representations of words from the dataset. The model uses a global average pooling layer to turn the sequence of embeddings into a single, fixed-size vector. This layer averages values across the time steps, summarizing the entire sequence into one representation. Doing this reduces the dimensionality of the data and makes it easier for later layers to process. By pooling over time, the model captures the overall context of the input sequence, which is important for tasks such as text classification. We add a dense layer with 8 units that uses the ReLU activation function to the model. This layer applies a nonlinear transformation to the pooled input, allowing the model to learn more complex representations. By introducing this nonlinearity, ReLU enables the model to capture more intricate patterns in the data. The final layer of the model is a dense layer that produces 2 output values or logits, one for each class. It takes the hidden layer's output and applies a linear transformation to generate these raw scores. We do not use an activation function here so that the outputs remain logits. These logits are then suitable for loss functions, such as sparse categorical cross-entropy, that are designed to work directly with raw class scores. We build a Keras model by defining its input and output layers. The input is a sequence of token indices that represents the text, and the output is a set of logits produced by the final dense layer. This input and output specification fully describes the neural network architecture. Once defined, the model can be compiled and trained for text classification tasks. We begin by compiling the model to prepare it for training. We use the Atom optimizer, which is a common and efficient choice, and a loss function called sparse categorical cross-entropy, which is designed for classification problems with integer labels and measures how far the predicted probabilities are from the true labels. The loss function is set to work directly with raw outputs from the model, since the final layer does not apply a softmax activation. We also track accuracy as a metric, so we can monitor how often the model predicts the correct label during training. We train the model using the Keras fit method, feeding it the padded input sequences along with their labels. The model is trained for 20 epochs, so it passes through the entire dataset 20 times. We use a batch size of 2, meaning the model updates its weights after every 2 samples. The verbose setting is turned off, so training runs without printing progress, allowing the model to learn patterns efficiently while keeping the output silent. The model is evaluated on the same small dataset it was trained on by computing loss and accuracy. The loss indicates how closely the model's predictions match the true labels, and the accuracy shows the fraction of predictions that are correct. This evaluation is run silently, without displaying intermediate output, by turning off verbose reporting. We report the final loss and accuracy values to evaluate how well the model performed. The loss is the cross-entropy loss, and we round it to 4 decimal places to make it easier to read. We also round the accuracy to 4 decimal places, giving a clear, concise summary of the model's performance on the training data. To make a prediction, the model first processes an input example and produces raw output scores called logits. These logits are not yet easy to interpret, so they are passed through the softmax function provided by TensorFlow. Softmax converts the logits into a set of probabilities that sum to 1 across all possible classes. This gives a clear probability distribution that reflects the model's confidence in each class. The code first shows the predicted probabilities for the first example in the dataset by converting the model's raw output scores, called logits, into probabilities using the softmax function. These probabilities represent how confident the model is that the example belongs to each possible class. It then prints the true label for that same example, which is the actual class it belongs to. Comparing the predicted probabilities with the true label helps us see how well the model performs on this specific instance. We start by converting the first label to an integer to get the index of the correct class for the first example. Using this index, we look up the model's predicted probability for that true class. We then compute the manual cross-entropy loss by taking the negative logarithm of this probability, adding a tiny constant, so we never take the log of 0. This manual loss calculation lets us check that the model's own reported loss for the first example is correct. The code calculates the cross-entropy loss by hand for the first data example and prints this value. It then compares this manual result with the loss produced by the model to check that the model's computation is correct. Before printing, the manually computed loss is rounded to 4 decimal places to make the output easier to read and interpret. This script shows how cross-entropy loss is used in a simple text classification task with TensorFlow. It builds a tiny sentiment dataset of positive and negative sentences, converts the text to padded integer sequences, and feeds them into a basic neural network with an embedding layer, pooling, and dense layers that output logits for 2 classes. The model is trained with the atom optimizer and sparse categorical cross-entropy loss, then evaluated on the same data to report loss and accuracy. Finally, the script predicts probabilities for one example and compares the model's cross-entropy loss to a manually computed value, confirming that the loss calculation is consistent and illustrating how cross-entropy behaves in practice. Ignoring padding tokens. When training text models, we often batch sentences of different lengths by padding shorter ones with a special token so they all have the same size, which is efficient for hardware. However, these padding tokens do not contain real information, so treating them like normal words in the loss function can mislead learning. If the model is penalized for predictions on padding, the gradients become distorted and training quality suffers. Just as you would not grade a student on blank space at the end of an answer, the model should ignore padding positions during training. When training models, it is important to ignore padding tokens when computing the loss and focus only on real tokens. This is done by using a mask that marks which positions are valid and which are just padding. For example, in sentiment analysis, padding added to make a short review match a fixed length should not influence learning because it carries no sentiment. By excluding these padded positions from the loss, the model learns only from meaningful words and does not waste effort on irrelevant placeholders. When working with sequences of different lengths, such as news articles or legal documents, it is important to ignore padding tokens during training. If padding is included in the loss, it introduces noise that can dominate the loss and gradients. This pushes the model to learn patterns from irrelevant padding instead of the real text. By excluding padding from the loss calculation, you get cleaner gradients, more stable training, and a model that focuses on meaningful content and generalizes better to real inputs. Python code. Ignoring padding tokens. This script demonstrates how padding masks work in a simple text classification model. It builds a small classifier that processes sequences containing padding tokens. During training, the loss is computed while ignoring these padding tokens, so they do not affect learning. This shows how padding masks help the model focus only on meaningful input data. The commented line recommends installing TensorFlow version 2.20.0, which is a specific release of this machine learning library. Choosing an exact version helps keep the code compatible with the library's features and behavior. This avoids problems that might occur if newer versions introduce changes that the existing code does not expect. Specifying versions in this way is a common practice in software development. We begin by importing 3 key libraries. The operating system library lets us work with files and environment settings. The random library gives us tools to generate random numbers and make random choices. Finally, we import NumPy, a numerical computing library that helps us handle arrays and perform mathematical operations efficiently. We start by importing TensorFlow, a main library used for machine learning and deep learning. Next, we bring in Keras, a higher-level interface within TensorFlow that makes it easier to build and train neural networks. We also import the layers tools from Keras, which provide components like dense and convolutional layers for designing network structures. Together, these imports give us the core tools needed to create and train our text classification model. To make our results reproducible, we set a fixed seed value of 42 for all sources of randomness. We first apply this seed to the standard random module, so its random operations are consistent across runs. We then use the same seed for the NumPy random number generator to keep its random outputs aligned. Finally, we set TensorFlow's random seed to 42 as well, so operations like neural network weight initialization behave the same each time. Using one shared seed across these libraries ensures uniform, repeatable results, which is important for debugging and comparing model performance. This line of code prints the version of TensorFlow currently in use. It provides a quick check that the correct version of the library is installed and running. Confirming the version helps ensure compatibility with your code and makes debugging easier when something does not work as expected. We begin with a small dataset of short text samples, where each phrase is a simple movie review used to train a text classification model. The dataset includes a few clearly positive phrases, such as good movie and great film, and a few clearly negative phrases, such as bad movie and terrible film. By training on these examples, the model can learn to distinguish positive from negative sentiment based on the words that appear in each phrase. We represent the sentiment labels as a NumPy array of zeros and ones, where 1 indicates a positive sentiment and 0 indicates a negative sentiment. Each label in the array matches a specific text sample, telling us whether that text is positive or negative. We set the data type of this array to 32-bit integers, so it works smoothly with TensorFlow operations used later in the workflow. We build a dictionary that assigns each word a unique integer index, so text can be converted into numbers for machine learning models. A special padding token is given index 0, and then words like good, movie, great, film, excellent, acting, bad, terrible, and poor are each assigned their own increasing index values. This mapping from words to numbers is what allows the model to process and learn from text data. In this setup, the maximum sequence length is fixed at 4 tokens, so every text input is either padded or cut off to have exactly 4 tokens. Using a uniform length for all inputs is important because it lets the neural network process data in batches. This consistency simplifies training and evaluation, since the model can handle each input in the same way. We convert each piece of text into a sequence of numbers so it can be used by machine learning models. For every text, we split it into individual words or tokens and look up each token in a predefined word index dictionary. If a token is not found, we assign it the value 0, which usually represents padding. We then collect these numeric indices into a sequence for each text and store all such sequences in a list, giving us a fully numerical version of our text data. We use Keras preprocessing to pad encoded sequences so they all have the same length, which is set to 4 in this example. Padding tokens are added to the end of each sequence, a method called post-padding. The padding value is 0, which matches the pad index in the word index mapping. Making all sequences uniform in length is important because it allows efficient batch processing in neural networks. We convert the padded sequences into a NumPy array with an integer 32 data type, so they are in a format that TensorFlow can process efficiently. TensorFlow operations often expect specific data types, and using this integer format matches those expectations. This step helps ensure that data flows smoothly into the model training pipeline without type-related issues. For training, we first make sure that the number of input sequences matches the number of labels, so each sequence has a correct target. We then verify that every sequence has the required length, defined by the maximum sequence length. This check ensures that all sequences are consistently padded or cut to the same size, which keeps the model input uniform and reliable. We start by finding the vocabulary size, which is simply the number of entries in the word index dictionary and represents all unique words the model can recognize, including the padding token. We then choose an embedding dimension of 8, meaning each word will be mapped to an 8-element vector in the embedding space. This embedding size is a tunable hyperparameter that can be adjusted depending on how complex the model needs to be. We begin by defining an input layer in Keras that accepts sequences of integers with a fixed length. These sequences are then passed to an embedding layer, which converts each integer into a dense vector with a chosen dimensionality. The embedding layer is set up to ignore padding tokens by enabling masking, so these padding values are not taken into account during training or evaluation. This setup allows the model to focus only on the meaningful parts of each sequence. We use a global average pooling layer on the output of the embedding layer to summarize the entire sequence into a single vector by averaging values across the sequence dimension. This operation captures the overall pattern of the input while naturally ignoring padding tokens. As a result, the model can handle sequences of different lengths in a consistent way and learn from the real content without being affected by the padding. We add a dense layer with one output unit as the classification head, using a sigmoid activation function that produces a probability between 0 and 1 for binary classification. Next, we define a Keras model by specifying its input and this output layer, which sets up the overall architecture. The model takes the pooled features from the previous layer and outputs a probability that represents the sentiment of the input text. The model is now being compiled, which prepares it for training. It uses the Atom Optimizer, a common and efficient choice for updating model weights. The loss function is binary cross-entropy, which is appropriate for binary classification because it measures how far the predicted labels are from the true labels. During training, the model will also track accuracy, giving a simple measure of how often its predictions are correct. The model is trained using a fit procedure that takes input sequences and their labels and runs for 10 epochs, so it passes through the entire dataset 10 times. A batch size of 2 is used, meaning the model updates its weights after every 2 samples. training is set to run silently with no progress messages. In addition, about 1/3 of the data is held out as validation data to monitor the model's performance during training. This code checks how well the model performs on the training data by using Keras to compute its loss and accuracy on the given inputs and labels. The evaluation runs silently because progress messages are turned off. The resulting loss and accuracy values serve as final metrics that show how well the model has learned from the training data. We report the final training loss, rounded to 4 decimal places, to summarize how well the model has learned to classify the text data while ignoring padding tokens. We also report the final training accuracy, rounded in the same way, to show how often the model's predictions match the true labels. Together, these two values give a clear, concise view of the model's overall training performance. The code first uses the trained model to generate predictions for the input data without showing any progress messages. It then prints the padded input sequences, which are the original text inputs converted into uniform-length numeric form. Finally, it prints the predicted probabilities for each sequence, showing how confident the model is that the sentiment is positive or negative, with the values rounded to 4 decimal places for easier reading. This script shows how to handle padding in a TensorFlow text classification task. It uses a small set of text phrases with binary sentiment labels, converts each phrase to integer sequences using a word index, and pads them to a fixed length with a special padding token. A simple neural network with an embedding layer that masks padding, followed by global average pooling and a sigmoid output layer, is trained with an atom optimizer and binary cross-entropy loss. After training for several epochs, the model's loss and accuracy are evaluated to confirm it has learned to ignore padding. Finally, it prints the padded sequences and their predicted probabilities to illustrate how the model processes and classifies the input data. Measuring model accuracy. When training a text model, you need a clear way to measure performance beyond just watching the loss go down. For classification tasks, accuracy is a common metric because it tells you what fraction of examples the model labels correctly. For each input, the model predicts a label. You compare it to the true label and count it as correct or incorrect. The number of correct predictions divided by the total number of examples gives a simple percentage that summarizes how well the model is doing, and is easy to communicate, even to non-experts. When training a model, we track accuracy on both the training and validation sets to see if it is truly learning rather than just memorizing. High training accuracy alone can be misleading because the model might overfit by capturing noise in the training data. Validation accuracy is therefore crucial, as it reflects how well the model generalizes to new, unseen data. For example, if a spam classifier's training accuracy keeps improving, but its validation accuracy stops improving or gets worse, that is a warning sign of overfitting and poor performance on future emails. When judging model accuracy, you must consider the task and data. For balanced tasks like sentiment analysis, accuracy works well, but for rare events such as toxic comments, accuracy alone can be misleading. In those cases, you should also look at precision, recall, or the F1 score to better evaluate performance on minority classes. Track accuracy and loss over training epochs, and check both training and validation results. A well-behaved model will show loss going down and accuracy going up on both sets, then leveling off at a good balance for real-world use. Python code, measuring model accuracy. This lesson uses a very small text classification example to show how to measure model accuracy. The main goal is to demonstrate, in a simple and clear way, how to compute accuracy for predictions. By focusing on this basic scenario, you can see exactly how correct and incorrect classifications are counted. This helps you understand the core idea of accuracy without getting distracted by complex details. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It forces the environment to use this exact version, so the code runs as intended and avoids compatibility problems with other versions. This kind of command is usually executed in a Jupyter notebook or a similar tool that can run shell commands directly. We start by importing 3 key Python libraries. The operating system library lets us work with files and environment settings. The random library gives us tools to generate random numbers and make random choices. Finally, the NumPy library supports fast numerical computing, especially for working with arrays and performing efficient mathematical operations. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layer components from Keras, so we can assemble different kinds of layers, such as dense or convolutional layers, to form the structure of our model. We begin by setting a fixed seed value of 42 so that any random operations in our code give the same results every time, which is important for reproducibility. We apply this seed to the random library, to the random number generator in NumPy, and to TensorFlow's random operations. By seeding all 3, we ensure that every source of randomness in the script behaves consistently across different runs. We start by printing the version of TensorFlow that is currently in use. Knowing the exact version helps confirm that the environment is set up as expected. This is especially important when sharing code with others or when troubleshooting issues that may depend on specific TensorFlow versions. We begin with a very small text dataset made up of short phrases, each labeled as either positive or negative in sentiment. This tiny dataset is used only to keep the examples simple and to focus on how we measure model accuracy. The phrases include basic expressions such as good movie and terrible film, which are typical in sentiment analysis tasks. Using this compact set of examples makes it easier to illustrate the overall process without extra complexity. We use a NumPy array to store binary sentiment labels for our text dataset, where each label is 0 for negative sentiment or 1 for positive sentiment. The array is explicitly defined to use integer values, so the labels are treated as whole numbers. This integer format is important because many machine learning models require numerical input in this form to work correctly. We use a text vectorization layer from TensorFlow Keras to turn text into numbers so it can be used by a machine learning model. This layer is limited to a vocabulary of 20 tokens, meaning it will work with up to 20 distinct words. It outputs sequences of integers that represent the text. Each input is converted into a sequence of exactly 4 integers, with shorter text padded and longer ones truncated to fit this fixed length. The vectorizer is first adapted to the small text corpus by processing the given array of text samples. During this step, it learns the vocabulary and basic structure of the data. It builds a mapping from words to integer indices, usually based on how often and in what order words appear. Once this mapping is learned, the vectorizer is ready to convert new text into numerical sequences that can be used as input to a model. We start by turning the list of text samples into a TensorFlow dataset so the text can be handled efficiently. Then we pass each text entry through the text vectorization layer, which converts it into a sequence of integers that the model can work with more easily. Finally, We group all these integer sequences into a single batch, using the total number of texts as the batch size, so they can be processed together in one step. We begin by turning the dataset of integer sequences into a NumPy array by taking the first batch from the dataset iterator and converting it using the NumPy method. This step gathers all the sequences into a single array. Doing this conversion is important because it puts the data into a format that works smoothly with the rest of the machine learning pipeline. In particular, it makes the data ready for model training and evaluation. We first check and print the shapes of the input data and labels to make sure they match what we expect. This confirms that each set of input features lines up correctly with its target label. Doing this simple check helps catch alignment problems early and prevents errors later during model training. It is an important validation step before moving on to building and fitting the model. We begin by splitting our data into two parts, one for training and one for validation. The first portion of the input data is used as the training set, and the remaining entries form the validation set. We do the same split for the labels, so that each input has a corresponding label in either the training or validation group. This setup lets us train the model on one subset, and then evaluate its performance on a separate subset, helping to avoid biased results based only on the training data. We build a simple text classification model using the sequential interface in Keras. It starts with an embedding layer that turns each input token into a small, dense vector, with a limited vocabulary and short fixed-length sequences. A global average pooling layer then averages these vectors across the sequence to remove the time dimension. Finally, a dense layer with one neuron and a sigmoid activation outputs a probability for binary classification, making this a basic setup for predicting a yes or no outcome from text. The model is now being compiled, which prepares it for training. It uses the atom optimizer, a common choice that works well for problems with sparse gradients. The loss function is binary cross-entropy, which is appropriate for binary classification tasks. The model also tracks accuracy as a metric to measure how well it performs during training and validation. We train the model using the Keras fit method with input sequences and their labels as training data. The model runs for 10 epochs, meaning it goes through the entire training set 10 times. We use a batch size of 2, so the model updates its weights after every 2 samples. The verbose setting is turned off, so training runs without printed progress. We also supply validation inputs and labels, so the model can check its performance on unseen data after each epoch. To assess model performance at the end of training, we look at the last recorded training accuracy in the history, which shows how well the model fit the training data. We do the same for validation accuracy by taking the final value from the validation accuracy history. This final validation accuracy indicates how well the model generalizes to new, unseen data. Together, these two values help us evaluate both learning on the training set and performance beyond it. We report the model's final training accuracy and round it to 3 decimal places so the value is easy to read and interpret. We then do the same for the final validation accuracy. Presenting both rounded values side by side makes it simple to compare performance on the training data with performance on the validation data. To evaluate the model on the validation set, we first obtain a probability for each sample that reflects how confident the model is that the sample belongs to the positive class. We then turn these probabilities into binary predictions by comparing each one to a threshold of 0.5. If a probability is at least 0.5, we label it as 1 for a positive prediction. Otherwise, we label it as 0 for a negative prediction. Using these binary labels allows us to compute standard accuracy measures for the model's performance. To manually compute accuracy, you compare each predicted label with the true label and count how many predictions are correct. Then, you divide this count of correct predictions by the total number of validation samples. The result is the proportion of correct predictions, which is the manual accuracy of the model. We manually compute the validation accuracy and print it, then compare it with the accuracy reported by the model. We round this value to 3 decimal places to keep it clear and easy to read. This comparison checks that our manual calculation matches the model's metric, helping confirm that the model's reported performance is correct. This script shows how to measure model accuracy using a simple text classification example. It first fixes random seeds for reproducibility, then uses TensorFlow to convert a small set of text samples into integer sequences and split them into training and validation data. A basic neural network is built with an embedding layer, global average pooling, and a final sigmoid layer, and is trained with binary cross-entropy loss while tracking accuracy. After 10 training epochs, the script reports the training and validation accuracies, and also manually computes validation accuracy by comparing predicted and true labels. The 2 accuracy values match, confirming the model's performance on this small dataset. In this lecture, you learn to use nn.Embedding to convert token indices into dense vector representations, build a simple sequence model, e.g. RNN or CNN, for text classification in PyTorch, and train and evaluate the text model on a labeled dataset, monitoring accuracy and loss. In the next module, Module 7, we will go over torch.compile and speed.
Thank you for your attention. See you all in the next lecture.